New materials play a crucial role in shaping the future of technology and innovation. They have the potential to revolutionize industries ranging from healthcare to energy. In fact, according to a report by Grand View Research, the global advanced materials market size is expected to reach $1.63 trillion by 2027, reflecting the growing demand for innovative materials. One fascinating aspect of new materials is their ability to exhibit unique properties that traditional materials lack. For example, carbon nanotubes are incredibly strong and lightweight, making them ideal for applications in aerospace and automotive industries. Another interesting fact is that the development of new materials can lead to significant environmental benefits. By creating materials that are more durable and energy efficient, we can reduce waste and minimize our carbon footprint. The field of material science is constantly evolving, with researchers exploring novel ways to manipulate the structure and properties of materials at the atomic level. This level of precision allows for the design of materials with tailored functionalities, such as superconductivity or self-healing capabilities. The impact of new materials extends beyond technological advancements. They also have the potential to improve the quality of life for individuals around the world. For instance, the development of biocompatible materials has revolutionized medical implants and prosthetics, enhancing patient outcomes and quality of life. As we continue to push the boundaries of material science, the possibilities for innovation are endless, paving the way for a brighter and more sustainable future. Physics plays a fundamental role in the development of new materials, providing the underlying principles and tools necessary to understand and manipulate the behavior of matter at the atomic and subatomic levels. One of the key concepts in physics that is essential for material development is quantum mechanics. This branch of physics deals with the behavior of particles at the smallest scales, where classical physics no longer applies. Quantum mechanics has led to the discovery of phenomena such as superconductivity and quantum tunneling, which have paved the way for the development of novel materials with extraordinary properties. For example, superconductors, materials that can conduct electricity without resistance, are based on quantum mechanical principles and have revolutionized various technologies, including magnetic resonance imaging, MRI machines, and particle accelerators. Another fascinating aspect of physics and material development is the use of computational modeling and simulations. These tools allow researchers to predict the behavior of materials under different conditions, saving time and resources in the experimental process. In fact, according to a study published in the journal Nature Materials, computational methods have become increasingly important in material science, with over 50% of research papers in the field now involving some form of computational modeling. The integration of physics and materials science has also led to the emergence of new interdisciplinary fields, such as nanotechnology and photonics. Nanotechnology, for instance, focuses on manipulating materials at the nanoscale, where quantum effects dominate, leading to the creation of nanomaterials with unique properties. Photonics, on the other hand, explores the interaction of light with materials to develop advanced optical devices, such as lasers and photonic sensors. The synergy between physics and material science has resulted in groundbreaking discoveries and innovations. For instance, the development of metamaterials, engineered materials with properties not found in nature, has opened up new possibilities in cloaking devices, high-resolution imaging, and telecommunications. According to a report by Research and Markets, the global metamaterials market is projected to reach $1.7 billion by 2025, driven by the demand for advanced materials in various industries. As we delve deeper into the realm of physics-based material development, we are unlocking the potential to create materials with unprecedented functionalities and applications, shaping the future of technology and science. Physics principles form the foundation of material science, providing insights into the behavior of matter at the atomic and subatomic levels. One key principle is quantum mechanics, which describes the behavior of particles at the smallest scales. In material science, quantum mechanics is essential for understanding phenomena such as superconductivity, where materials exhibit zero electrical resistance at low temperatures. This remarkable property has led to the development of superconducting materials used in applications like magnetic resonance imaging, MRI machines, and particle accelerators. Another important physics principle in material science is thermodynamics, which governs the energy transformations within materials. For instance, phase transitions, such as the solid-to-liquid transition, are dictated by thermodynamic principles. Understanding these transitions is crucial for designing materials with specific properties. Statistical mechanics is another key physics principle used in material science. It provides a framework for predicting the collective behavior of particles in a material based on statistical averages. This principle is particularly useful in studying the properties of materials at the nanoscale, where quantum effects become significant. The study of materials at the nanoscale has led to the development of nanomaterials with unique properties, such as enhanced strength and conductivity. One fascinating application of nanomaterials is in the field of nanomedicine, where nanoparticles are used for targeted drug delivery and imaging. In addition to quantum mechanics, thermodynamics, and statistical mechanics, the principles of solid-state physics play a crucial role in material science. Solid-state physics focuses on the properties of solids, including their electrical, magnetic, and optical behaviors. For example, the study of semiconductors, a class of materials with intermediate conductivity, has revolutionized electronics and led to the development of devices like transistors and solar cells. The field of solid-state physics has also contributed to the discovery of new materials with exotic properties, such as topological insulators, which conduct electricity only on their surface. These materials have the potential for applications in quantum computing and energy-efficient electronics. The integration of physics principles in material science has enabled researchers to design materials with tailored properties for specific applications. For example, metamaterials are engineered materials that exhibit properties not found in nature, such as negative refractive index. These materials have opened up new possibilities in optics and telecommunications, leading to advancements in lens design and signal processing. According to a report by Markets and Markets, the global metamaterials market is projected to grow at a compound annual growth rate of 21% from 2021 to 2026, driven by the demand for advanced materials in various industries. The principles of physics continue to inspire innovative approaches to material design and synthesis, pushing the boundaries of what is possible in material science. One remarkable case study of successful material development using physics is the discovery of graphene, a two-dimensional material composed of a single layer of carbon atoms arranged in a hexagonal lattice. Graphene's exceptional properties, such as high electrical conductivity and mechanical strength, have made it a promising candidate for various applications. In 2004, Andrei Geim and Konstantin Novoselov isolated graphene using a simple method involving adhesive tape and graphite, for which they were awarded the Nobel Prize in Physics in 2010. Since then, graphene has been explored for applications in electronics, energy storage, and biomedical devices. According to a report by Research and Markets, the global graphene market is projected to reach $568.7 million by 2026, driven by the demand for advanced materials in electronics and composites. Another fascinating case study is the development of high-temperature superconductors, materials that can conduct electricity without resistance at relatively high temperatures. In 2015, researchers at IBM successfully synthesized a high-temperature superconductor based on a class of materials called cuprates. This breakthrough opened up new possibilities for practical applications of superconductors in power transmission and magnetic levitation. According to a study published in the journal Nature, high-temperature superconductors have the potential to revolutionize energy storage and transmission systems, leading to increased efficiency and reduced energy losses. One more intriguing case study is the discovery of metamaterials, engineered materials with properties not found in nature. Metamaterials are designed to manipulate electromagnetic waves in unconventional ways, leading to applications in cloaking devices, antennas, and sensors. In 2006, researchers at Duke University developed the first metamaterial with a negative refractive index, allowing for the bending of light in the opposite direction of natural materials. This discovery paved the way for advancements in optics and telecommunications. According to a report by Markets and Markets, the global metamaterials market is expected to grow at a compound annual growth rate of 21% from 2021 to 2026, driven by the demand for advanced materials in aerospace and defense. These case studies demonstrate the power of physics in driving innovation and pushing the boundaries of material science, leading to the development of materials with extraordinary properties and applications. Developing new materials comes with its fair share of challenges and limitations that researchers must navigate. One significant challenge is the high cost and time investment required for material discovery and development. According to a report by the National Science Foundation, the average timeline for bringing a new material from concept to commercialization can range from 5 to 20 years, with costs reaching millions of dollars. This lengthy and expensive process can hinder the pace of innovation in the field of material science. Another challenge is the limited understanding of complex material behaviors at the atomic level. Many materials exhibit properties that are governed by intricate interactions between atoms, making it challenging to predict and control their behavior accurately. This lack of fundamental understanding can impede the design of materials with specific functionalities. Additionally, scalability and reproducibility pose challenges in the mass production of new materials. While a material may show promising properties at the laboratory scale, scaling up production while maintaining those properties can be a daunting task. This issue is particularly relevant in industries such as electronics and energy storage, where consistent material performance is crucial. Furthermore, regulatory and safety considerations add another layer of complexity to the development of new materials. Researchers must ensure that new materials meet stringent safety standards and environmental regulations before they can be commercialized. Balancing innovation with safety and compliance requirements is a delicate process that requires careful consideration. Despite these challenges, the field of material science continues to push boundaries and overcome limitations through interdisciplinary collaboration and technological advancements. Recent research trends in material science have been focused on the development of smart materials that can respond to external stimuli. One exciting area of research is the exploration of shape memory materials, which have the ability to remember their original shape and return to it when triggered. These materials have applications in aerospace, robotics, and biomedicine. Another emerging trend is the development of self-healing materials that can repair damage autonomously, mimicking biological systems. Researchers are investigating various mechanisms, such as microcapsules containing healing agents, to enable materials to self-repair. In the field of nanotechnology, researchers are exploring the use of nanomaterials for environmental remediation. Nanoparticles have shown promise in removing pollutants from water and air, offering a sustainable solution to environmental challenges. Quantum materials, which exhibit exotic quantum phenomena, are also a hot topic in current research. These materials, such as topological insulators and quantum spin liquids, have the potential to revolutionize electronics and quantum computing. According to a report by Allied Market Research, the global smart materials market is projected to reach $27.7 billion by 2027, driven by the demand for responsive and adaptive materials. The field of material informatics, which combines materials science with data science and machine learning, is also gaining traction. By leveraging big data and computational tools, researchers can accelerate the discovery of new materials with targeted properties. The integration of artificial intelligence and high-throughput experimentation is streamlining the material discovery process, leading to faster innovation and breakthroughs in material science. Experimental techniques play a crucial role in material characterization, allowing researchers to probe the structure and properties of materials at the atomic and molecular levels. One widely used technique is X-ray diffraction, which involves shining X-rays onto a material and analyzing the diffraction pattern to determine its crystal structure. X-ray diffraction has been instrumental in the discovery of new materials, such as high-temperature superconductors and zeolites. Another powerful technique is scanning electron microscopy, SEM, which provides high-resolution images of a material's surface. SEM can reveal details as small as a few nanometers, making it invaluable for studying nanomaterials and biological samples. In fact, according to a report by Markets and Markets, the global electron microscopy market is expected to reach $2.7 billion by 2025, driven by the demand for advanced imaging techniques in material science and life sciences. Raman spectroscopy is another versatile technique used in material characterization. By measuring the scattering of light, Raman spectroscopy can provide information about a material's chemical composition and molecular structure. This technique has applications in pharmaceuticals, forensics, and environmental monitoring. In the field of material science, nuclear magnetic resonance (NMR) spectroscopy is widely employed to study the interactions between atomic nuclei in a material. NMR spectroscopy can reveal information about molecular dynamics, chemical bonding, and material purity. According to a study published in the journal Science, NMR spectroscopy has been instrumental in the development of new materials for energy storage and catalysis. These experimental techniques, along with others like atomic force microscopy and transmission electron microscopy, continue to drive advancements in material science by providing valuable insights into the properties and behavior of materials. The future prospects of physics-based material development are promising, with the potential to revolutionize various industries. One exciting area of research is the development of quantum materials, which exhibit unique quantum phenomena like topological insulators and quantum spin liquids. These materials have the potential to enable faster and more energy-efficient electronics. According to a report by Research and Markets, the global quantum materials market is projected to reach $3.9 billion by 2025. Another emerging trend is the use of machine learning and artificial intelligence in material discovery, known as material informatics. By leveraging big data and computational tools, researchers can accelerate the development of new materials with tailored properties. This interdisciplinary approach is expected to drive innovation and lead to the creation of advanced materials with unprecedented functionalities. Recent research in material science has focused on smart materials like shape memory materials and self-healing materials. Nanotechnology is being explored for environmental remediation, while quantum materials show promise in revolutionizing electronics. The integration of material science with data science and material informatics is accelerating the discovery of new materials. Experimental techniques such as 10-ray diffraction and Raman spectroscopy play a vital role in material characterization, providing valuable insights into material properties. Exciting advancements in material science are on the horizon, with quantum materials projected to reach a market value of $3.9 billion by 2025. The integration of data science and material informatics is driving innovation. Let's continue exploring the endless possibilities in physics-based material development.